Okay, class, in the last video I said that each pair of inverse functions contains only one co-function. We're actually going to look at what we mean by a co-function. The inverses are not co-functions. They are such that each pair of inverse contains only one co-function. The co-functions are tied together based on their names. So if you think, for instance, about the sine, and then its co-function is cosine. Or if you think about the tangent, and its actual co-function is the cotangent. Okay, so that's how you tie the co-functions together. What this tells us, and it's an obvious result if you look at what we just learned about right triangle trigonometry. So let's say that I wanted the sine of B, angle B here, the sine would be the opposite, which is B, over the hypotenuse, which is C. Now let's take a look at its co-function as it relates to the angle over here, A. The co-function is the cosine, and if I look at the cosine of not B, but A, the opposite of A is now, the opposite of angle A is now A, and the cosine is the adjacent over the hypotenuse. So the adjacent to A is the same as the opposite of B, so we're going to put B over C. Notice that's the same result. So the co-functions are the same for complementary angles. B plus A are complementary angles because within the triangle the total sum of all the angles is 180 degrees, and since this right triangle that's 90 degrees, that leaves 90 degrees for B and A to add to. And that's how we develop our co-functions. So if I take the co-function of the other angle in the right triangle, then I get the same result. Let's look at tangent here as an example. So the tangent of A should be the same as the cotangent of B. Okay, these complementary angles, A and B. And if I look at either one, the tangent of A would be the opposite over the adjacent. So from A's perspective, that's A over B. And so I should expect to get the same result for the cotangent of B. So the cotangent is going to be the adjacent over the opposite. And for B, the adjacent is A, and the opposite is B. So the 2 is A over B. Okay, and that leads us to this complementary angle theorem. So co-functions of the complementary angles in the right triangle are equal. Okay, let's put this new idea together with some examples here using the co-function. So I know that I need a complementary angle for 62 degrees. So complementary angles add up to 90. So if I take the 90 and subtract the 62, I'll have a complementary angle of 28. These are all degrees. Okay, and I know that the co-function, the complementary angles are equal. So whatever the sine of 62 degrees is going to be the same as the cosine of 62 degrees complement, which is 28 degrees. Okay, here we have, in terms of radians, 90 degrees is represented as pi over 2. Okay, so if I take pi over 12 and add it to the complementary angle, I would get pi over 2. So if I take the difference from pi over 2 and pi over 12, okay, so I need a common denominator here. So I'm going to write pi over 2 as, so I would get 6 pi over 12 minus pi over 12. So 5 pi over 12 the complement to pi over 12. And I know that the cofunction for tangent is cotangent. So the cotangent of 5 pi over 12 would be equivalent to the tangent of pi over 12. Okay, this next one I'm just going to look at this. Okay, so the complement of 50 degrees is 40 degrees, right? So I'm going to take the sine square of 40 degrees and add to it, instead of another sine, I'm going to write the cosine squared of the complement of 50 degrees, which is 40 degrees. And since I've got the same angle, we're looking at the Pythagorean identity where that equals 1. So this just simplifies to 1, which we can see if we substitute the cofunction with its complementary angle from sine to cosine.